Okay, good afternoon, everyone. So we'll have the 15 Power and Energy webinar. This one will be about digital twin and machine learning based operation and maintenance solutions for photovoltaic power plants. We'll have two speakers today. The first one is Christian Merrique. He has a master's degree in electrical engineering from the University of Casino in southern Malaysia. Have a background on power electronics, renewable energy, and AI, about renewable energy systems. And right now is a project manager at EDP New. Is the coordinator of the project AI for PV, which is a Eureka project with two countries involved, Portugal and Spain. So from the Portuguese side is EDP New, the coordinator, and INESC TEC. And so the presentations that we'll see today is part of the results from the project. The project have much more results to show, and actually you can go to the LinkedIn page or website of AI for PV, and you'll see there a workshop that we'll do in the end of the project to show all the results from the project that goes beyond this webinar. So the presentation of Christian will be about AI for PV, so AI applied to operation and maintenance of PV parks, and we'll show what EDP New is developing in the project. Then we'll have a second presentation from Loelson Costa about the framework of the digital twin for PV inverter and integration with machine learning algorithms. So Loelson have made a bachelor, master, and doctoral degree from the Federal University of Campina Grande in Brazil. Have been visiting Virginia Polytechnic Institute and also worked in the Federal University of Rio Grande do Norte in Brazil, and is since 2021 is a senior researcher at INESC TEC, and have been applying AI for power electronics, mainly in the context of renewable energy power plants like PV, the AI for PV project. So just a remark, the goal of these webinars is to present research ideas, research results. In general, we have a presentation from INESC TEC and then a presentation from an external speaker, and everyone is open to contact us. You can, if you want to make a presentation on these webinars, you can send an email to energywebinars.inesctech.pt. I will put this email in the chat, or you can visit the website of the webinars, and there is there a form that you can fill, and you can submit a topic to present. So we are always open to presentations from anyone, and of course we want to keep promoting these webinars. Okay, so now I pass the word to Christian.
Thank you, Ricardo. Thank you for the introduction.
While Christian changes the slides, just a remark I wrote on the chat. If you have any questions, please put them on the Q&A window. Don't put them on the chat, and we'll take questions after each presentation. Okay, thank you.
Thank you, Ricardo, for the introduction, and thank you for inviting me to this really interesting webinar. So today I will be presenting you one of the solutions we developed as EDP New within the AI for PV project. So before we start, I want to give you a brief background of the project itself. So AI for PV is a collaborative project with the seal of the Eureka cluster. We have a consortium of 3 partners coming from 2 different countries, so Portugal and Spain. We have EDP New, which is the company I work for, that is the project coordinator, and EDP New is the R&D center of EDP, the Portuguese utility. Then we have INESC TEC, this well-known R&D institution, still from Portugal. And finally, we have Isotrol, which is an ICT company from Spain, specializing in monitoring system for renewable energy power plants. So the objective of the project was to develop digital twin and AI solution to enhance the operation and maintenance of PV parks. So by integrating these 2 technology, we wanted to have robust solution in order to detect and classify possible failures of the PV park at early stage, and also to reduce underperformance. On top of these two layers, we also developed a task recommendation engine that is used to support O&M teams in finding the optimal policy that brings the highest revenue to the operators. Today, I will be presenting you one of the solutions we developed, which is the cleaning module that is used to optimize the cleaning schedule of PV parks. So we base our model on a Markov decision process, which is a mathematical framework that is used to model decision-making problems where the outcomes are random and partially controllable. In a Markov decision process, we have different parameters. We have the S, which is the set of states that describe the status of your environment. Then we have A, which is a set of actions that the agent can take. We have T, which represent the transition matrix, the transition function that tells us how what's the probability of moving from one state to another, taking a certain action. We have the reward, which is what the agent receives when taking a certain action, being in a certain state. And finally, we have gamma, which is the discount factor that is used to control the trade-off between immediate and future rewards. Now we will see how these apply to a PV power plant. So in our case, the environment is a PV power plant, which can be described as a finite horizon MDP. We use the finite horizon description because we want to simulate the entire lifetime of the PV park, so the whole time span. The state, in our case, represent the level of the performance ratio or the soiling rate, because we want to optimize the cleaning schedule, as I said, and the actions that the agent can take is either to clean or not to clean the PV panels. Then we have the transition probabilities, which, as I said, are used to, let's say, compute the probability of moving from one state to another when you take a certain action. And in the case of soiling, we can describe this phenomena through a non-homogeneous Markov chain. So these probabilities here are dependent on different variables like cleaning decisions, whether you have cleaned or not cleaned the PV panels, but also are dependent on two natural phenomena, which are the deposition of dust on the PV panels and rain events. So basically, we need to compute these probabilities in the two cases, depending on the two actions. When we don't, in absence of cleaning, the transition probabilities can be retrieved through the formula we have here in the slides. Then we will see later on each one of these terms, what they represent. But basically here in this probability, we have two terms. The first one describes the transition probability in case of rain, while the second one is in absence of rain. In the case of cleaning, we assume a perfect cleaning, which means that after the cleaning campaign, the soiling rate will go to 0, regardless of the initial state you were in. So let's see all these terms. So as I said, the first term was describing the transition probabilities in case of rain events. So here we have two terms. The first one is represent the probability of rain in a certain epoch. So it's basically the probability of rain for a certain day for the region at stake. And we computed this from historical weather data of the site at stake. And here we should say that a rain event is considered as such when the accumulated precipitation is above a certain threshold, so that we can consider the rain as beneficial in terms of soiling. Then the second terms describe the cleaning effect of rains. So this matrix is retrieved by looking at the historical operational data of the PV plant during these rain events. And so in this case, we can compute the occurrences from moving from one state to another in the case of the rain events. The second term of the formula was used to represent the transitions in absence of rain. So here we don't have rain events, and this basically is used to model the soiling phenomena itself. In our case, in order to model this phenomena, we use the gamma process, which is a distribution that is commonly used to describe the degradation processing. And a gamma distribution is characterized by two key parameters, the shape parameters and the scale parameters, which determine the rate at which the degradation occurs, and also the shape of this distribution. So we retrieve this data from the historical data, operational data that we have for the PV plant at stake. So we computed basically the average daily degradation due to soiling. Then another key terms for an MDP is the reward, which is what the agent receives when it takes a certain action under being in a certain state. And this depends on whether you have cleaned or not your PV panels. So in absence of cleaning, this reward was the revenues lost due to the soiling rate, while in the case of cleaning, it's the cost of cleaning itself. So here, as we can see in the formula, we have this term here, which describes the per irradiance price that you have. And instead of, let's say, sampling individually these two variables, we decide to sample the pairs so that we can capture the interdependence between the two variables itself. So we came up with this PD day distribution that we use in order to assess the reward. Then once we have defined our MDP, the ultimate goal is to find the optimal cleaning policies, which is the one that minimize the revenue losses to soiling. So here, what we need to do is to minimize this objective function here, which is the sum of all the rewards the agent received in each time step, given the action he took in that time step. So basically here by minimizing the cost function, we retrieve the optimal policies, which is a sequence of actions that the agent must take in order to minimize these revenue losses. So in order to validate our model, we compare it with one of the, let's say, most common strategy used in PV parks, where you basically define the cleaning policy looking at the performance ratio. And whenever the performance ratio is below a certain threshold, you trigger a clean event. So in order to validate it, we perform a CBA with the sensitivity analysis, where we vary the price of cleaning, and also we vary the different value of threshold used for what we call the traditional method. Here in this slide, we have the results we got when in the MDP process, you don't consider the rain. So we are just modeling the soiling phenomena itself through the gamma distribution. And we can see, for instance, that if the cost of cleaning is 3,000 euros per watt peak, our method can be more profitable for the operators, let's say, regardless of the threshold that you compare it with. But of course, this difference is there is difference in the revenue gain that you can earn. In this second slide, instead, we did the same CBA, but considering the MDP where also the rain events is considered. And we can see, as we can see here, for instance, our model compared to the threshold-based one, where the threshold is 70%, can bring 4% additional revenues to the operator. Finally, we also compared the two MTP problems where you consider or not consider the rain, and we can see that considering the rain can bring additional revenues to the plant owners, which vary from 0.6% to 1%, depending on the cost of cleaning. And I think this concludes my presentation. Thank you for your attention. If you have any question, I would be glad to answer.
Thank you, Christian. So if you have any questions, you can put them here in the Q&A window, but if you also want to make the question live, you can raise your hand and then I give you permission to make the question. So as I told, we will take questions now for the presentation of Christian, so don't be shy. And while everyone have to write or raise the hand, I think we have already one hand raised. So it's Bijus, so I will allow you to talk. I think now you can make the question. I think you are mute. Okay. And if you can hear us, you can make the question, but you have your micro mute. Okay, so while it doesn't solve the problem, okay, we have someone else. With Ali, I think you can talk, you can make the question, but you have to mute yourself. Okay, apparently it's not working. Okay, so in that case, it's better to use the chat, and I'll make the question myself. So there is already here a question. The first question is: do you have standards for cleaning at regular intervals, or it is a cost-effective over plant life cycle?
Yeah, I should say that one of the other traditional methods that is used in order to define the optimal cleaning schedule is to clean the PV panels on a, let's say, fixed time interval. But sometimes this is not the best strategy to pursue in order to increase your revenue. So our model, what tried to do is the opposite. So it trying to define the optimal policy regardless of the time interval between two consecutive cleaning campaign. So it's like that you are cleaning the PV panels looking at a variable threshold. So as I presented before, we compared it with a threshold-based model, where basically the threshold that you set to trigger the clean campaign is fixed, so it's always the same values. While with our model, we notice that we have this variable threshold, so that you can really optimize your revenue. So I would say that our models try to go beyond these common approaches, trying to resolve all the drawbacks that we have with these traditional approaches, which basically at the end of the day does not provide you the optimal policy.
Okay, so by the way, I have one question about that. We have more questions here, but so here you just try to make a simulation to see if to define this optimal policy. You don't plan with this methodology the cleaning, or do you expect to plan? I mean, for next day to find the optimal period to make the cleaning. Is that the final goal?
Yeah, this is the final goal. So on a daily basis, we run our model considering the current state, and we can tell the operator when it should clean the PV panels in order to get the maximum benefit.
Okay. So another question from Giang Pam is, can you elaborate on the gamma process using your research?
Yeah, let me just go back to the slide. Yeah. So as I said, this gamma process is a distribution that is used to is frequently used to model degradation phenomena. And basically here, what you do is you compute the probabilities that you have from moving to one state to another, considering what is the average degradation rate that you have. So we compute this daily average degradation rate from the historical operational data we have from the PV park at stake. And it depends on this ratio, but also on the time since your last cleaning. So that, it's like you have a moving, let's say, gamma function that moves towards lower states the more you don't clean your PV panel. So the probability of going towards state with lower performance ratio increase over time.
Okay, so another question from an anonymous attendee is if this is something you can run over any database or if this is specific of Isotrol.
Well, I would say that this approach can be used to any other database and power plant that you have at stake. But of course, what you need to do is to retrieve all these parameters and tailor these parameters to your own power plants. Because for instance, as I shown before, we also take into account the energy price. So this is something that depends on the geography as well as the reagents also depends on the geography and so on. So the overall approach can be used for any other use case, let's say, but still you need to fine tune the parameters to your own case.
Okay, another question, if this will be commercially available. So what is your plans in terms of exploitation?
Yeah, I mean, our idea is to, first of all, improve the tool itself, because we find some room for improvements still, and then we would like to validate it more, so even beyond the project itself, and then integrate it in our own power plants. Since I mean we are an energy utility, so we would like to leverage from this.
Okay, so one question from Shrey Verma is how optimization is different from the digital twin. You just described optimization. I guess this is the part of presentation from Noelson, but yeah, I will let you clarify that.
Yeah, I mean, Noelson's presentation will complement my answer, but here we use optimization because we also need to kind of predict what will be the future behavior of the power plant. So it's an optimization over a multiple time step. Yeah, I mean, it's different from the digital twin in the sense that we are putting into play also probabilities that you don't really have, let's say, in digital twins. And the ultimate goal here is to optimize the policy for the whole lifetime of the project. So from, let's say, today until the commissioning date that you have. So also the duration of the optimization problem will impact on your optimal policy.
Okay, so we have one question from Pedro Benedicto that is if you have used reinforcement learning to solve this decision problem, and if yes, which framework or algorithm have you used?
Yeah, here I should say that our initial intention was to use reinforcement learning, but at the end we didn't, because the problem was quite complex in the sense that here everything is changing in time and also depending on the action that you take. So we couldn't apply, let's say, standards reinforcement learning algorithms, like, for instance, policy iteration and so on. So we did solve the problem through optimization itself, so through mixed, integer, linear, non-linear programming. So we wrote the problem as an optimization problem itself, still considering the MTP framework.
Okay, thank you. So I don't know if we have more questions, still have time for more 2 or 3 questions, or to test if someone raises the hand, I can put them talking. So you still have a few minutes. Otherwise, if there is no more questions, we can move to Noelson, and in the end, we might take more questions to Christian. So you can still think on more questions to Christian while Noelson presents. Okay, since we don't have any questions here, I think we can now go to Noelson that will talk about digital twin and machine learning. Noelson.
Okay, so let me get to screen. Okay, are you guys seeing full screen, I guess?
Yes.
Okay, so thank you, Bessa, for introduction, and Christian for the first presentation. And on my presentation, I'll be talking about the framework of a digital twin of a PV inverter and the integration in machine learning algorithms. Because, as Christian mentioned, the PV plant has multiple subsystems, and some partners of the project are working, for instance, on the transformer, others are working on the PV modules itself. And thus, from CPAS at INESC TEC, we are working mostly on the PV inverter. And of course, we have to work a little bit with transformer and PV modules too. But our main tool of study is the PV inverter. From the CPAS side, we have a very good team work on that, on the PV inverter, which is composed of Ana, José, Olga, Ricardo, and Professor Rui. And my name is Loel, so I'll be doing the presentation for today. So this is a brief summary of the project, of the presentation. We'll be discussing a little bit about introduction and contextualization. Then we move to the digital twin itself, a brief look at the fault classification, conclusions, and some references if you want to study a little bit more on the subject. And also, as Christian mentioned, the results of those webinars of these presentations are from the AI for PV project, which, as the name suggests, we're trying to apply AI solutions to improve the performance of PV systems, in that case, a PV power plant from EDP. So for the introduction, we usually, when you think about PV power plants, you think about the PV modules, the converter, and the grid connection. But actually, there are multiple other subsystems on the PV power plant, and all of them are prone to failure. So we can have the PV modules, combiner boxes, converters, sometimes more than one. We have the filters, we have the connection to the grid, we have the communications. It might be the case of some PV power plants having some battery banks, etc., etc., etc. And every one of those equipments, they are prone to failure. Some are more severe, some are more lighter. But if we're going to list all of the failures, we would need a full webinar just to discuss all of the failures that can happen on this PV power plants. On our side, on the CPAS power energy side, we'll be focusing more on the power electronics converter, which is a central asset of the PV power plants. So our solution, at the end of the day, this is speaking as a whole for the project, but of course, with the focus on the PV inverter, is to provide insightful information to the PV power plant operators and maintenance staff, provide insightful information about the current state of the PV power plant. If everything is working as intended, fault-free condition or no fault condition, that's okay. You don't have to worry about it. But if we have some deviation, for instance, in the current voltage, power factor, frequency, if we have some deviation on some of those measurements, that might be an indication of a problem that is occurring on the PV power plant. And then this is where our digital twin combined with our AI models will work on this data and evaluate it to make sure, okay, this is not a fault, this is just a deviation out of normality, a sensor problem, or this is actually a fault at the junction boxes, a fault inside of the inverter, a fault on the PV models, or a fault on the transformers, etc., etc. And our idea is not to replace the operators, but actually to support them with those tools to make sure that this multitude of data, of measurements, power, frequency, voltage, current, etc., to support them by doing this first analysis of the data. If there is something strange with the PV power plant, we can provide some leads. We can say there is a problem at this point of the PV power plant. This started in this morning, and the power losses are X%, and then the operator can start the maintenance right away on that subject or equipment under failure right away. And when we look back at the project, remember that this is the outcome of the project, we came up with some building blocks from the solutions that we have developed. So basically, we start with a data set, which is provided by EDP and Isotrol, as the Isotrol is doing the logistics and the data manipulation for us and provide us the data. And the data itself is from a PV power plant from EDP. So they are sharing this data with us, which is composed of meteorological and SCADA data, which are basically electrical measurements. Then we have a block that we're calling rewrite, which is the reordering and data cleaning. This is just a data pre-processing. Then we have the digital twin itself, which is done on Simuli, MATLAB Simuli, where we do the no-fault validation, then we do some fault simulations too. After that, we have the hybrid dataset, or how we are calling it, which is composed of real data from the real asset and some synthetic data generated by the digital twin. The data form at this moment is time series, and also on this stage, we're doing some feature engineering, which is an iterative process with the machine learning algorithms, where we are doing the models tuning, training, testing, and models comparison. So at the end of the day, we can summarize that we are starting from an Excel sheet or CSV file, whatever. We go over all of those building blocks all over this pipeline until we arrive at a classification problem, multi-class classification problem, which can be represented by a confusion matrix. So for the digital twin itself, I would like to start with the definition of digital twin, which was first introduced by Michael Greaves, 2002. This guy is very active on LinkedIn, for instance. It's very interesting to follow him on LinkedIn. But he says that a digital twin is a virtual representation of a real-world entity processes which are updated, synchronized, which are synchronized at a specified frequency and fidelity. And the digital twin must have three basic elements: a real space containing a physical object, a virtual space containing a virtual object, and a link of data flow from virtual to real space and vice versa. And the classical example is a car and a real car and the virtual car. So the real car is on the real space. We have some data that is acquired by sensors on the car, which is sent to our virtual space. Our virtual space can be a big system composed of multiple subsystems. The subsystems can be simulating multiple different occurrences from the real asset, generate some insightful information, including doing fault classification, which is our case. And after that, we return this information back to the real asset, in that case, a car, but in our case, will be providing the operator with some information that we have found using our digital twin and machine learning algorithms. So when we move to our PV power plant, if we compare the definition of the digital twin, we can say that our physical object is a PV power plant from EDP, the one called Monte das Flores. Our virtual object is a Simulink simulation, which contains the PV strings, junction boxes, the inverter itself, power transformer, grid, and control, and sensors, etc., etc. And a link for data flow between those two assets, between the real and the virtual asset. So we receive data from the PV power plant. We process the data, do some simulation, do the classification, and send this information back to the operator of the PV power plant. And how do we know that our model is good? Our model, or I mean, our digital twin is good enough. What we did, we built a simulation, as Christian mentioned, tailored for this solution, tailored for the PV power plant of Monte das Flores, and then we did a comparison between the real data that we had and our simulation data. And when we compare the real data, which is the blue one on the top plot, and the simulated data, which is the orange one on the top plot, where we're calling no-fault simulation, we can see that we have somewhat of a good result. Of course, this is only for a single day during the summer, but we have tested it for multiple days of the years, multiple months, and even multiple years, as we have a lot of data available. And at the bottom plots, we have the root mean square error that we can see that our model is not as good as expected during sunrise and sunset, but during most of the day, it has a good behavior. And we found that would be good enough so we can move on with our studies. This was for a good day during the summer, but we also evaluated for multiple other days, including winter. So we can see that during winter, our performance is a little bit worse, but it's not that bad. And then at the end of the day, we don't want to build a perfect model. Of course, we want to get a 0% error, but this is not achievable. So we tried to go to the best model as possible as we could achieve using the data that we have available. So even during summer or winter, autumn or spring, we find that our model is good enough. even though it has a general worse performance during the winter. So we find that the lower the radius, the worse our model be performance, even though it's not a bad model for the simulation. After we have this data, we started playing around with the faults and failures. And before discussing it a little bit, I'd like to bring the definition of fault failure, detection, diagnosis, which when we started studying this research line, we saw that fault and failure is something for some people and is another thing for other people. The same goes for detection and diagnosis. So we started defining what is fault and failure, detection, diagnosis, or borrowing the definition from reference 5. You can check more on that later. So basically, a fault is a condition where the asset is still working, but is not, let's say, working at 100% capacity. And the failure is when the model is not working at all, or the asset is not working at all, because it is a problem that is so severe that that part of the system has to stop. The same, similar definition is done for fault detection and diagnosis, where the detections is saying if there is a fault or not on the system. Usually this is the first step of a fault diagnosis. And following fault detection, there are multiple steps like identification, isolation, etc., until we achieve the fault diagnosis, where we're gonna say the type of fault, the time where it occurs, etc., etc., etc. So at the end of the day, we'll be discussing here the classification, but the final objective of the project is the fault diagnosis. So for the faults that we have implemented so far, as for the first slides, we saw that there are multiple faults and failures that can happen on the PV power plant, on multiple equipment that we have on the PV power plant. But focusing on the inverter or around the inverter, we came up with some faults to be implemented on our digital twin. So we have the switch degradation, switch open circuit. Those are very common faults because the inverter is one of the equipment where that presents the most number of failures on the PV power plant. So compared to PV models and transformer, the inverter is much more susceptible to failures. And we also have implemented some short circuit faults between phases, a DC cable degradation, and a DC cable open circuit. We chose those faults because they are one of the most common that happens on PV power plants around the inverter. Of course, if we're going to evaluate the faults on PV models, there are a whole other new faults that we can be implemented here. But at this point, we are focusing on the inverter or around the inverter. And then we did the simulation of these multiple conditions of our inverter to see how it would behave. So what we can see here is for the same day, we simulated multiple conditions for the inverter. We have the real asset, the real data, which is the original data, let's call it that way. And then we have DC cable degradation, open circuit, short circuit, switch degradation, switch open circuit. And what we can see here is that, for instance, we can easily spot that the DC cable short circuit, let me get my pointer. I can't see it. Okay, mouse pointer. Okay, we can see that the DC cable short circuit is easily distinguished from the other conditions. But when we go to the right-hand side figure, we can see that the switch degradation and the short circuit between phases of the inverter is not as easy to distinguish from switch degradation, for instance. So our idea was, okay, if we're going to look only to the DC current, might not be enough to classify all of the faults. We can classify some of them, but not all of them. Then we start to take a look on the DC link voltage. So we measure the DC link voltage for those multiple conditions, and okay, on this case, the DC cable short circuit is easily distinguished as was on the current, and maybe to help a little bit more to distinguish between switch degradation. I don't know, for the MPPT fault is very easy to distinguish from the DC link voltage. So let's take a look at the AC power. So the AC power shows that it's easier to distinguish from the short circuit between phases and the switch degradation. So what is the idea of our machine learning models? We're feeding to the machine learning models multiple measurements, not only DC current and voltage and AC power, but actually AC currents, AC voltage, frequency, power factor, PV currents, PV voltage, etc. We are feeding multiple measurements to our machine learning models so they can do this classification, so they can differentiate one condition to another and do the classification of the PV power plant, saying, okay, right now there is no problem with the PV power plant, but at some point we might have an MPPT fault, or we might have a switch open circuit fault, etc. This is what our machine learning models are doing right now. And then for the fault classification, I'm already finished, I'm not sure about the time, but for the fault classification, what we have is basically, we have what we're calling the raw variables, which are the inverter measurements and the weather measurement, or SCADA measurements, current, voltage, power, and the weather measurements, temperature and pyranometer, or irradiance measurements, and also some feature engineering that we find that were important to improve the accuracy of our model. So for the calendar variables related to time, daily sky types related to the cloudiness of the day, and some mathematical derived features, which are the lagged measurements and the statistical data considering variance and mean. For the classifier, we are splitting the train test data set on 80-20%. We tested multiple machine learning models, random forest, light gradient boosting, position regression, etc. And then we did the feature selection, hyperparameter tuning. Keep in mind that this is all iterative process. We tried something, then we obtained some results. Okay, let's discuss it with our team from electronics engineer, electrical engineers, AI specialists, etc. And then we test out of the sample set from multiple days. And the output of our results is a multi-class classification. At this stage, we only considering 5 conditions, but at the end of the project, we're considering 8 conditions, 3 more compared to this one. And for the explanation, we have those output classes, which is the no fault condition, or the healthy or fault-free condition of the inverter. We have the DC cable degradation, or DC cable open circuit, and we have the switch degradation, or switch open circuit. So when we started trying to do the classification of those faults, we started with a simpler model, which was the logistic regression. We achieved an accuracy around 80%, not that bad, but we considered that we could improve it a little bit more. So we started studying and moved it to random forest, and we get an accuracy of 95%. Okay, not bad. But then we tried the light gradient boosting machine, which provide results as good as the random forest one, but with a smaller computational load. So right now, we are considering the light gradient boosting machine the best model so far. And then when we start to deeper investigate the light gradient boost machine, we move from 96% accuracy to 98% accuracy when we added some feature engineering features, considering time, the lags, and the statistics. So right now we are sitting around 98% accuracy. Of course, at this stage, this is, let's say, only for the digital twin, only considering the digital twin of the inverter. So this is closer to an ideal scenario, but when we do the integration with the whole system, it's very likely that this accuracy will be reduced a little bit. Also, I would like to highlight over here that is kind of hard to do the differentiation between the no fault and the DC cable degradation, because we can see that for the other conditions is almost perfect, but when we are talking about the no fault of DC cable degradation, is a little bit harder to do the classification, and we find that this is because the DC cable degradation is often misclassified as a no fault condition under lower irradiance. So we concluded that the DC cable degradation is the trickiest one to do the classification. And actually, the DC cable degradation is basically an intermediate state between a healthy condition, a no-fault condition, and a DC cable open circuit. But yeah, we achieved some good results. The worst one is for the DC cable degradation, but it's not that bad. And for conclusions, what else could be done? So from this presentation, what we're working on is also the fault diagnosis, explore more faulty scenarios or other faulty conditions, and also randomly generate or weather-related or weather-dependent faults. So at the end of the day, the faults might be randomly appear. Of course, they have some cause, but they might be just randomly appear on the data, or they might be related to weather conditions. So this is what we're going to explore in the future. So the faults can happen based on some condition of the atmosphere or humidity or gradients, etc. Is it applicable to other renewable energy sources? Yes, as we have the ambition to explore those methodologies to wind power and batteries and etc. And similar to what Christian explained to one of the questions, this solution is tailored for the Monte das Flores PV power plant. But the methodology that was applied can be exported to any PV power plant. Of course, the difference might be the power level of another PV power plant, the configuration of this other PV power plant. All of that must be taken into consideration when developing the digital twin. But the methodology or those building blocks that I have showed on the beginning of the presentation, they can be applied to any PV power plant and on our ambition to any other renewable energy source. And what can be further explored? As you saw, we are using most of the softwares to be open source. Most of the scripts that we have developed are on Python, but we're still dependent on MATLAB Simulink to do the digital twin. So one of our future work, let's call it that way, is to move to open source solutions for some software that can replace Simulink to do the simulation of the PV inverter and the PV models and the transformers, etc. Also, another, let's say, ideas that we have is the novel representations of the data of the system as a whole. For this presentation, we saw that the data is represented as a time series, but we have already a publication that represents the data as an alpha, beta, or Clark transformation representation, and we are also thinking or use graphs to do the localization of the fault. So my idea, the discussion here is that this is a very rich field of research. We are developing some solutions for the FAPV project and other future projects, but there is also a lot of innovative solutions that can be developed, and we are also working on that, even with some publications already. So that's it for me, Bessa, thank you. There are some references at the end of the presentation if you want to study a bit more about it, but that's it. Now we are open for questions, I guess.
Thank you, Wilson. So we already have here 2 questions, and we still have 10 minutes to conclude, so we can take more questions. So I will start with the first one is, how can the digital twin track changes in PV assets? For example, we might buy new PV devices in the physical world. So if you have new devices add to the PV power plant, for example.
Okay, so in that case, if there is a new device to be added to the PV power plant, whoever developed the digital twin, you have to take a look, talk to the operators of the PV power plant, and they'll explain, okay, the new modifications on the PV power plants are the addition of new PV models, or the allocation of the PV models or junction boxes, or we are adding a new inverter to the PV power plant. Whichever modification the real asset is going through must be communicated to whoever is developing or maintaining or operating the digital twin, so they can do this modification on the digital twin as well. If there is a mismatch between the real asset and the digital twin, the results provided by the digital twin and the classification models, for instance, that we have developed here, might not be correct. So the digital twin must be as close as possible to the real asset. Whichever modification is done to the real asset should be done to the digital twin, so we can keep the track of those changes.
Thank you. So another question from Panos Papadopoulos is that the question is, what is the contribution of your approach towards the digital twin platform or framework? And how this is different from a model that is just fed with real-time data from the field.
Okay, so if I understood the question, Panos, basically what we're doing with this approach of detailing the inverter is that we can also include the classification of faults related to the inverter or inside the inverter to our classification problem. Usually, when we're going to study the papers that we have around there, that we have out there, what they are doing is considering the inverter or sometimes the whole PV power plant as a black box. So the classification is going to be basically input power versus output power, or input current voltage versus output current and voltage. And what we're doing right on this project over here is using the power of MATLAB Simulink to do a more detailed model of the inverter, so we can do failures, for instance, inside the inverter. The MPPT failure is a failure that is inside the inverter because it's related to the control of the inverter. The switch degradation, switch open sequence is also inside of the inverter. And usually what we have is some simpler model that they are good enough to do a detection, for instance, but they are not good enough to do a classification. So at the end of the day, some of the solutions that we have out there, they're gonna say, okay, there is a fault on the PV power plant, but I cannot give any more details because the model is not detailed enough. This is the difference that we're bringing with the digital twin. We can say there is a fault on the PV power plant at inverter 1 or inverter 2 or junction box 1, 2, 3, whichever, and the fault might be caused by some other reason. And we can say the location, when the fault occurred, and from other tools of the project, we can say you should change, you should replace the inverter now, or you can wait a little bit more, and etc., etc. So basically, what we're bringing new to this project is do a more detailed approach to the inverter itself.
So I think something to add also, Wilson, is that with these we are able to simulate events that were not observed in the field data, and I think this is an important point. So allow us for simulate different faults in the PV inverter, and then with this synthetic data we can train machine learning algorithms to classify and localize those faults. So it's more than just digital twin that replicates the normal operation of the system, but allow us to explore different operating modes or different faults that were not observed with the data collected from the real system. Okay, so another question from an anonymous attendee: if you have an idea of how many faults did you have in the data set, so the percentage, for example?
Okay, for this data set specifically for Monte das Flores, we didn't have any big faults to study. Mostly some small maintenance stops and something like that, but we didn't have any fault from this Monte das Flores, which is actually very common PV power plants. One of the difficulties of studying this research area is that it's very unusual to have a fault on the PV power plant. But when they happen, there is a lot of power production loss. But I didn't get any of this data, I'm sorry, but I know that, let's say, from the whole faults, the multiple faults that can happen on a PV power plant, I would say that 40 to 50% of those faults happens on the PV inverter. And the other 50% is distributed between sensors or communications or PV modules, etc., etc. So one of the motivations for us to do such a detailed study of the inverter was that it's a central asset of the PV power plants that is not studied as much as are the PV models, for instance, which are also very important, but the inverter are not explored as much as the PV models. So they are responsible for most of the faults of the PV power plant, but are not studied as much. This is one of the motivations to do a detailed study on the PV inverter. I didn't bring any data about the percentage specifically, but on the references, you can find this information easily in one of the papers.
Another question from Ravi Kishore, I hope I pronounced it correctly, is if there is any reason to use MATLAB Simulink plus Python and not just using MATLAB.
Okay, Ravi, thank you. Yeah, we started using only MATLAB Simulink because MATLAB, we were using the MATLAB scripts to do the data cleaning and we can also use that to do the machine learning models. But our goal at the end of the day, it was to move to open source solution. So at the beginning of the project, that building blocks slides was mostly Simulink, MATLAB. And right now we're moving to try to use MATLAB as less as possible, because we want to be not dependent on some licensed software such as MATLAB Simulink. But yes, we can do everything inside MATLAB Simulink, but that has a cost. And now we're trying to move to open source solutions, but we haven't found a good enough replacement for the Simulink to do the simulation of the inverter itself. So that's why we are using Python at the beginning and at the end of the pipeline, but at its core, there is still MATLAB Simulink.
Okay, one more question from Javi. One is if there is studies exploring separating algorithms for the edge or cloud deployments. Yeah,
there are studies about it. We have this ambition, but we haven't implemented this just yet. But there are some studies where people are, for instance, embedding the digital twin on an FPGA and deploying it to be as close as possible to the inverter. So instead of going through the sensor, the SCADA system, an API for download and upload of the data, there are some solutions where people are deploying edge computing to be as close as possible to the PV inverter, but we haven't developed it on this project yet, but we have this ambition, but this is gonna be our work to months to come still.
And then this third question is the time granularity of the input variables that we have used.
Okay, Javi, so the time granularity was 15 minutes because this is I think it's the lowest granularity that they can achieve on EDP Monte Flores, because as this PV power plant was already in operation, and then we arrived to test our solution. So they already have this 50 minutes granularity, and this is how we deployed the solution. So of course, if there is a problem, it's gonna take at least 50 minutes for us to detect. If we could use, for instance, edge computing, and for instance, have access to the firmware of the inverter, we could be as close as possible to real time. So every second, I don't know, or every fraction of second, if we have access to the firmware and we are using edge computing, we can achieve a granularity even smaller. But right now, for this solution, for this project, is 50 minutes.
Thank you. So we don't have more questions, and we are also reaching the 1 hour duration. So let's thank. I would like to thank Loelson and Christian for all the effort in preparing these presentations, and also to Daniela for organizing this webinar, and it was a very interesting session. So see you in the next one. As I mentioned, you can propose presentations in the website. So there is the question if we'll share the presentations. We'll share after this the webinar. We'll share the video with these presentations, and the video will also be available in the YouTube channel of INESC TEC. Okay, so it will be in the website and in our YouTube. And as I mentioned, so we'll have the workshop, it's in the chat, of the AI for PV on the 28th of June. And there is more presentations from other partners and from other researchers involved in the project. Christian and Loelson are two of the researchers, but there is more. So you have on the chat the link also to LinkedIn, where you have the registration link. And you can also find it in the website of the project as well. Okay. Thank you. So,
thank you, everyone. Bye-bye.
Good
one.
Yeah,
Thank you, everybody. Bye-bye.